Continuing on, 6.1, we're going to spend a third day introducing something called ordinary points. Take a look at the very top. We have a second order differential equation. If we divide out our lead coefficient, we'd have y double prime plus p of xy prime plus q of xy equals 0. Looking green though, a very important definition. A point is said to be an ordinary point if both p of x and q of x are analytic at x naught. X naught is a very important point. It means that that's where your series would be centered. Analytic means P and Q can be written as a series centered at x naught. A point that's not an ordinary point is said to be a singular point of the differential equation. The singular point is something we're going to study in great detail in our next section in 6.2. Well, take a look at this example here. Y double prime plus e to the x y prime plus sine of x equals 0, or sine of x times y equals 0. X equals 0 is an ordinary point. E to the x and sine of x both have power series that are centered at x equals 0. And those are the ones we referred to in a previous video, ones that you should have memorized. Take a look at this next example. Xy double prime plus sine of xy, we could divide everything in this equation by x. You might wonder if sine of x over x is analytic at x equals 0. Could we make a power series centered at x equals 0? Yes. We've got sine of x is x minus x cubed 3 factorial plus x to the 5th over 5 factorial. That's up here. But we could divide everything by x. And we'd have a power series for that centered at x equals 0. In other words, it's a Maclaurin series. However, take a look at the natural log of x. You cannot get a power series centered at x equals 0. As you're trying to create that, first of all, you're not going to be able to have one of the memorized forms that we've used in the past. But even as you try to generate it through derivatives, you would get, unfortunately, undefined values. So we're not going to have a power series there. Now, in all truth, we're going to really spend a lot of time with polynomials out in front as coefficients. And deciding if a point is ordinary or singular is super important when we're going to be solving in this chapter. It will help us determine how to solve the differential equation. We'll have slightly different methods in 6.2, in other words. It's very difficult to do work for P and Q with some coefficients. Notice what I've underlined, it's relatively easy with polynomials. Here's why. If you look at this differential equation that we pretty much started off with, if that lead coefficient, if you plug in your point in question, your x value, x naught, and if it's not equal to 0 for that lead coefficient, then you're going to have an ordinary point. Now this is if all these coefficients are polynomials. You'll also have a singular point if when you substitute in x naught you get 0. So very quickly, just wanted to point this out for the sake of time. Find ordinary and singular points. Take a look at our first example, lead coefficient x squared minus 1. X squared minus 1 is equal to 0. What we're really getting at is solving, you'd get x equals plus or minus 1. These are our singular points. All other values of x are ordinary. Look right here, x squared plus 1. You might say, oh, these are imaginary solutions. You solve, you get x is equal to plus or minus I. True. We would still say that these are singular points. All other values of x are ordinary. Look at the Cauchy-Euler equation. We saw that before. Ax squared is our lead coefficient. Set that equal to 0 and solve. You'd get x equals 0. That's your only singular point. All others are ordinary points. Well, what's so special about ordinary points? If you have an ordinary point, x naught, And if you've divided out your lead coefficient, there are always two linearly independent solutions, each in the form of a power series centered at x naught. You call your two solutions y1 and y2. As a big hint, remember yesterday on the video, we saw that we came up with two series solutions. We're going to do that in just a moment as well. The general solution is going to be y equals c1 times y1 of x plus c2 times y2 of x. Well, the bulk of our time is going to have to be spent here, where we actually get into work here. First of all, notice that my coefficient out in front is just a 1, so we only have ordinary points. That's important for us to make a note of. But I'd like for us to solve for two series solutions centered at x equals 0. X equals 0 is an ordinary point. Like I said, the lead coefficient's just 1. So let's assume that that can be done. We'll have y equals n equals 0 to infinity of c naught, or c sub n, I should say, c sub n times x to the n. Y prime is going to go from n equals 1 to infinity. Remember, we're losing that first constant. Done that before, doing this now for the third time. We're going to take a second derivative. We're going to lose another constant. So we're going to go from n equals 2 to infinity. This time we're going to bring down an addition with that n, an n minus 1 and an x to the n minus 2. We'll substitute this all in, and we're just going to have to clean this all up, solve. Let's see, we'll have x squared times y. Well, our y is written pretty much just above where I'm writing. But very importantly, set this equal to 0. I'm going to recopy here. And by the way, sometimes kids will just immediately realize, hey, when I've got that x squared out in front, I'm going to have to bring that inside of sigma. And you want to do that. This is going to be x to the n plus 2. Set that equal to 0. Well, the name of the game here is re-indexing. This is k equals n minus 2. That's what I'd like my new power of x to be. Over here I'd like k to equal n plus 2. And my goodness, as we work through that, we'll have a new series. Hopefully one that's easier to work with. If n's equal to 2, plug 2 into this substitution, you'd get k equals 0. N itself would be k plus 2, so this is c sub k plus 2. And then n, like I said, was k plus 2. N minus 1 would be 1 smaller than that quantity, so that would be k plus 1. And n minus 2, that's the whole reason for this substitution. We'll have x to the k. This other substitution, if n's equal to 0, we'd get k equals 2. Of course, going up to infinity. N would be k minus 2, so this is c sub k minus 2. And again, we'll have x to the k. You can see immediately this looks so much better, and yet, even though both series have x to the k in them, sadly, our lower bounds are different. I've got k equals 0 to start off with on that first series. Tell you what, I'm going to let k equals 0 and then plug in k equals 1 and just pull those out to the front. Now if k is equal to 0, I'll have c sub 2. 0 plus 2 is 2. 2 is going to get multiplied to 0 plus 1, which is just a 1, so I'll just have a 2 there. And then the coefficient of x, that's x to the 0. How about I let k equal 1? We'd get look at these parentheses. 1 plus 2 is 3. 1 plus 1 is 2. 3 times 2 is 6. So that's 6 c sub 3. But this would be x to the 1. Well, that's great now that I've plugged in k equals 0, k equals 1. At this point, I'm at k equals 2. And I'm going to leave off with that because at this point, now I've got two series, both with the same lower bound, both with x to the k written inside. And that's fantastic news because now I can join them together. In other words, I can write, instead of two series, I'll just write one. So let's see if we could do that real fast. We will get 2c sub 2 plus 6c sub 3x. But now let's just write 1 sigma. Tell you what, I'm going to put some brackets in here. And I'm going to factor out x to the k. I'm going to pull that out of the brackets. And right now, so thankful that we've got 1 sigma instead of 2. But I keep pointing this out. The right-hand side says we have 0. That means that this right here, 2c sub 2 must equal 0. In other words, c sub 2 is equal to 0. 6c sub 3 would have to equal 0. That means c sub 3 is equal to 0 itself. Take a look at inside sigma. Very, very, very important right here. That must equal 0. So I'm going to have c sub k plus 2 times k plus 2 times k plus 1 plus c sub k minus 2. That must equal 0. I'm going to solve for c sub k plus 2. And I hope it's pretty obvious. You have to subtract c k minus 2 and then divide by those two parenthesis values. Alright. Well, at this point, I hope you can see we're going to start generating our coefficients. We've got k is equal to 2 as our first counter, our lower bound. I'm going to plug in k equals 2. You would get c sub 4. And up above, we're going to get negative c sub 2. Forgive me, that's not c sub 2. If I let k equal 2, you can see up on top, we'd get c sub 0. And what about down below? Well, if k is equal to 2, 2 plus 2 is 4, 2 plus 1 is 3, 4 times 3 is 12. Okay. Well, let's see. Let's let k equal 3. And again, this right here is what is going to generate all the values we're looking for. If I were to let k equal 3, we'd have c sub 5. 3 minus 2 is 1, so we'd have minus c sub 1. 3 plus 2 down below is 5. 3 plus 1 is 4. 5 times 4 is 20. Let's let k equal 4. We'd have c sub 6. K plus 2 would be a 6. Then we'd have negative c sub 2. Down below, 4 plus 2 is 6. 4 plus 1 is 5. We'd have a 30. However, c sub 2 is 0. Very important to point that out. This whole thing is 0. Let's let k equal 5. Well, if k is equal to 5, we'd have c sub 7. 5 minus 2 is 3, so we'd have negative c sub 3. Down below, we'd have 5 plus 2 is 7. 5 plus 1 is 6. 7 times 6 is 42. But again, c sub 3 is 0. So this whole expression collapses down to 0. Oh, what if we let k equal 6? We'd have c sub 8. And 6 minus 2 is 4, so we'd get negative c sub 4. And down below we'd have 6 plus 2 is 8, 6 plus 1 is 7, that's